Picture a satellite soaring around the Earth. You might expect it to trace a perfect circle. After all, gravity pulls equally in every direction from the center. But look closely. The real path is an ellipse. Stretched, lopsided, with Earth not at the center but off to one side. Why? What breaks the symmetry? Let's set up the problem. A massive body like the Earth sits at the center. A satellite orbits under the pull of gravity. The gravitational force is always directed inward toward the center, and its strength follows Newton's inverse square law. F equals gmm/r squared. That's it. One force, one rule. Now here's the key insight. A circular orbit is possible, but only if the satellite has exactly the right speed. At radius r, the required speed is the square root of gm/r. Too fast, and the satellite spirals outward. Too slow, and it falls inward. A perfect circle demands a perfect balance, and that's a razor-thin condition. So what happens when the speed isn't exactly right? Suppose we give the satellite a small kick, a tiny boost in speed. It now has too much energy for a circle at this radius. Watch, it swings outward, slows down, then falls back in and speeds up. The orbit stretches into an ellipse. Any deviation from that perfect circular speed produces an ellipse. Two quantities are conserved throughout the orbit. First, angular momentum. L equals mvr sine theta stays constant because gravity acts purely radially. Second, total energy, kinetic plus potential, is constant too. These two conservation laws lock the satellite onto an ellipse. They're the mathematical reason the orbit closes and repeats. Kepler figured this out centuries before Newton. His second law says the line from the planet to the satellite sweeps out equal areas in equal times. Near the closest approach, the periapsis, the satellite moves fast. Far away at apoapsis, it crawls. But the area swept per second, always the same. That's angular momentum conservation in disguise. Newton proved that the inverse square law gives orbits described by r equals p/1 plus e cosine theta. When the eccentricity e is 0, this is a circle. When e is between 0 and 1, it's an ellipse. The eccentricity depends on the satellite's energy and angular momentum, and since real launches never achieve e equals exactly 0, every real orbit is an ellipse. So a circular orbit isn't forbidden, it's just infinitely unlikely. Any real satellite, with any tiny imperfection in speed or direction, traces an ellipse with the central body at one focus. That's Kepler's first law, derived straight from Newton's gravity. The circle is the exception, the ellipse is the rule.